Okay, on the second lesson of this chapter, we're going to quickly talk about these four things. Okay, a sampling distribution, randomized distribution, statistical significance. All right, so this is a sampling distribution. So this is an illustration of this definition. Let's suppose you have a population and you want to take samples size, I don't know, 30. So you're going to take one sample size 30, and depending on what you're looking for, maybe you want to find the average household income of those 30 people. So I randomly select 30 families from New York State, figure out how much these families are making, and then average that. And let's say I get, I don't know, in thousands, 100. Grab another sample. They have to be the same size. Sample size 30. Let's say I find 110. Grab another random sample, size 30, and let's say I find, 200. Now what I'm doing, I do this an infinite amount of times. I plot all of these X bar values that I find on here. And what happens is, no matter how you do this, this actually turns out to be pretty close to a normal distribution, which happens by the central limit theorem. It's a very powerful statistical tool, and I'm running through this stuff really quick, but if you take stats or AP stats next year, we do this really slow, and we will be able to really dive into this topic, very powerful topic. So this is a sampling distribution of all these X bars. All right, that's kind of it in a nutshell. Now let me show you what it looks like on a computer. Try not to, it's a nice glare. Okay, so Reese's Pieces, all right. Let's say the probability of orange is 60%. I could change it, I could make it 70, I can make it 80, but let's say 60. And what I'm gonna do is I'm gonna sample 20 of these pieces, and I'm gonna figure out, now in here, I'm saying let 60% of these values be orange. And now I'm gonna grab 20 candies out of here, and I'm gonna see how many of them are orange. So see, it's doing this, the computer's randomly dropping in all the oranges. So the number of orange, it's not giving me the number of orange. Let me do this again. Okay, so it found 13 were orange, but I took 20 pieces out of there. So 65% of them were orange out of this one sample. Now if I do this again, let's see what happens. Oh, this one found 15 of them were orange. So 15 out of 20, 75% are orange. So now I'm gonna, but in this course, they usually talk about the proportion. So they're gonna put the percents down here. So I'm going to do this 100 times. Grab 20, find the proportion of orange, plot it. Grab another 20, find the proportion of orange, plot it. So all these values are the different amount of times that I've done that. Actually, let me do one again with the proportion. Actually, here, reset this. So it actually found 60%. Look at that. And it plotted it. Let's do it again. Oh, it found 70%. It plotted it. I'm going to do this 100 times. Well, I don't want to animate this. Boom. This is what happened. So if I were to do this 1,000 times, it pretty much almost becomes a bell curve. It almost becomes normal. And so that's the mean, and that's the standard deviation. So I took the mean of all of these values, and then I found the standard deviation of all these values. Now, how we got the standard deviation and the mean, we're not going to worry about that. But these are the numbers, okay? And this is a sampling distribution of proportions. I could do one of means if I wanted to, but... Okay, so in that example, it said that the mean was 0.604 and the standard deviation was 0.110. So there's something called a confidence interval. Confidence interval gives a range of plausible values. So if I wanted a 95% confidence interval, I need to go 2 standard deviations away from the mean. It's actually not 2, but in this course it's 2. If I wanted to do 3 standard deviations away, it would almost be 98% confidence interval, but they only do 95 in this course. So here's how you do it. Using these values, okay? So if I wanted a 95% confidence interval, I'm going to do the mean plus or minus 2 times the standard deviation. So it's the mean so this is my confidence interval. So whatever proportion I find, it should be within this interval. So any proportion I find should be within this interval. But if I find a proportion over here or over here, these outside of it are considered unusual. All right, very unusual that I would find something below that or above that, which makes sense. Like it would be pretty awkward to find 90% of them orange when only 60% should be. So if I see anything on the outside, I consider those results to be statistically significant. So any unusual results are considered to be statistically significant. Now, statistically significant means it was unlikely to happen by chance. You know, within the random assignment or within the random sampling, it was unlikely to happen by chance. Like, well, I doubt you just randomly found that. So what that means here, hang on. Give me a second. Trying to get this computer to do what I want it to do. All right, so here's an example. All right, the Reese's company says 60% are orange. I took 20 candies at a time, found the proportion of orange and plotted it. I did that 100 times. See this result here? That means on one sample of 20 Reese's Pieces, I found that 90% of them were orange. Look at how far away that is from this grouping here. Even that one, I only found 10% were orange. That means I picked 20 balls in here and 2 of them were orange. I wouldn't take that bet. So if you found that, those results would be statistically significant. It probably didn't happen by chance. So you know what that means? This is probably wrong. The Reese's Pieces company is probably off. It's not 60%, because if you easily found that, then I'm willing to bet that's a little bit lower, closer to your value. So that dot would be statistically significant. Something in here, well, that would probably happen by chance. I mean, you're likely to find that. It's kind of where it should be. These, no, unlikely to happen by chance. So that's a 95% confidence interval. All right, let's look at some examples. Now, I sent you guys a link of some questions, and in that link, it has a lot of old Regents questions. So right now, I'm going to work on number 391. If I had more time with this note sheet, I might have been able to utilize it a little bit better, but I only had 6 hours to get in, even less than that, to get in the building and just grab everything that I could on there. Okay, a group of students were trying to determine the proportion of candies in a bag that are blue. The company claims 24% are blue. Now, that's what the company claims, but the company could be wrong. See, just like the Oreos, people did studies on the double stuffed Oreo that it really wasn't double stuffed. It was like 1.8 stuffed. If I knew that before them, I would have sued. I would have called my lawyers. Been getting ripped off for years. Anyways, so assuming that 24% of the candies are blue, we had a computer run a simulation 100 times. So we told the computer programmer, all right, in your program, tell the computer that 24% are supposed to be blue. We're going to grab 50 at a time and then plot it. The proportion of blues. And we're going to do that 100 times. So there's 100 dots. So this dot right here, this is one sample, size 50, that had 30% of the candies were blue. This is one sample, size 50, that had 10% of the candies be blue. Look at how far away that is. Okay, that did not happen by chance. Those results are statistically significant. That means the company was probably wrong about that 24. Anyways, the simulation results in a mean of this and a standard deviation of that. Based on the simulation, what is a plausible interval containing the middle 95% of the data? So this is it. The mean plus or minus 2 times 0.60. So we have 0.254 plus or minus 1.2, which results in 0.134, 0.374. And here's something else you need to know. This value is called the margin of error. The margin of error. It's your give or take. It's going, all right, this is the mean, and we'll allow you give or take that much. That's the error that they're giving you. Now, if you shrink, that number 2, it's going to shrink that margin of error. If you make that 2 a 3, it's going to increase the margin of error. So let's actually look at this interval. See, if this is my interval, and this is not in the interval, because it's 0.10. So if I found this result, it would be statistically significant. Yeah, because it's not in the interval. So the company's claim of 0.24 is probably wrong. It's probably lower than that, but that's how you read these charts. 392, Mary bought a pack, they love candy. Mary bought a pack of candy. The manufacturer claims 30% are red. That's why around 30% you're gonna see most of the bubbles here, most of the dots. Same thing here. Here's 24%. That's why you're seeing most of these around here, because that's what your computer's finding. It's what it's doing for you. In her pack, 14 of the 60 candies are red. Well, 14 out of the 60, that's about 0.23. They call that p-hat. It's your proportion, about 23%. So 23%, all right, here's 25, here's 22 and a half, I don't know. 23% could be any one of these dots, all right? You could have found this one or this one, I don't know. She ran a sample of 300 samples, so there's 300 dots. And here's the mean, here's the standard deviation. Based on the simulation, determine a 95% confidence interval, so that's mean, plus or minus 2.058. All right, that's your margin of error, in case if they ask you that one. 0.417. 0.185. So anything in here, these are usual. These are usual values. All right, remember, these are unusual out here. So is Mary's pack unusual? Is p-hat equal 0.23 unusual? No. Because it's in the interval. So the company's claim is probably correct, because what I found is normal. Okay. Let's let me do this one. Number 397. Joseph was curious to determine if scent improves memory. I believe that it does. A test was created where better memory is indicated by higher test scores. A controlled experiment was performed where one group was given the test on scented paper. I wonder what scent it would be. And the other group was given the test on unscented paper. The summary statistics from the experiment are shown. Okay, so for the scented paper, they had an average score of 23 and a standard deviation of that. All right, I don't know how many people were in this group, but let's say there was 10 people in the group, and of those 10 people, they got 23 questions right. In this unscented paper, maybe there was also 10 people in this group, they got 18 questions right. Now, it looks like the scented paper that they are doing better, but is this difference enough to say that the scented paper is working? Or is it just, random that we would find that? So what we do is we tell the computer to generate what would happen 1,000 times, assuming that there was no difference. That's why it's 0. So we said, all right, assuming that there's no difference with the memory, we're going to let the computer run this experiment through. And that's why we get this graph. That's why the majority of them have the no difference. But now we look at our results, and we're going to compare it to the computer's. This is actually called a randomized distribution because they, instead of a sampling distribution, they did a randomized distribution. Randomized means they reran the experiment and plotted it, or a sampling distribution, they just grabbed from the population. So it's kind of the same thing, but I don't know, not really. So we found that they had a difference of 5. So this is what we found right here. That's pretty unusual. We should have found something in here. But because we found something out here, I'm willing to bet that Senate paper worked. We should not have been able to find that by dumb luck. Use a simulation to determine the interval representing the 95%, or the middle 95, 030 plus or minus 2, 1.548. Let me quickly do that. 2 times 1.548. Okay, so this is a range of usual values. I found 5. Okay, so is the difference in means in Joseph's experiment statistically significant? Yes, they are statistically significant. That means it could not have happened by chance. This probably didn't happen by chance because Joe found 5 and 5 isn't in the interval. So here's going a little bit further. The probability we would find 5 or results more extreme, like 5 or anything more than that, there's 3 dots out of 1,000. 3 out of 1,000 is 0.003. That's such a low probability that we should not have been able to do that. That's highly unlikely. Actually, in this course, any probability under 5% is unlikely. Thus, 95% confidence intervals. So that's how you handle these types of questions, and we're going to stop here.